Okay, hello everybody. This is Mr. Strauss. He's going to help with the lab we're doing today. So first, look at your notes, and I'm going to read you kind of the introduction part here. So this is the mole versus dozen lab, and it says when quantifying something, two main methods surface. One method is to refer to the amount of a substance by its mass or weight, i.e. a pound of rice or a pound of flour. Okay, so I've got a big bag of rice here. Now, if I was going to go to the store, I would not buy this rice and say, I need 1,000,000 grains of rice and expect someone to sit there and count it out. I'm going to buy it by the pound. Okay, flour or rice is quantified by mass, so we look at how much it weighs. For other substances, it's much easier to quantify by a number. For example, a dozen eggs or an apple. When I go to the store, I buy a certain number of apples. Okay. A dozen generally quantifies eggs or donuts or flowers, but in chemistry, we're dealing with really, really tiny particles, like an atom. So it's possible to quantify a substance by both a count and a mass. To understand a mole, so that's where this mole word comes in, we first think of a scale-up unit that we're already familiar with, such as a dozen. So think about a dozen. Why are donuts packaged by the dozen? Who knows? Why is it 12? I don't know. 12 seems to be a number that works well for selling and packaging donuts. But for us in chemistry, that would not work well, okay? We would have such a tiny, tiny number of stuff still, we wouldn't even be able to see it, okay? For a chemist, 1 dozen is still far too small. A dozen atoms of carbon, for example, would only have a mass of 2.39 times 10 to the negative 22nd. So that's you go touch the screen. 0.22 zeros, and then 239, okay? Way, way tiny. Even 1 billion carbon atoms are still too small to easily mass. If a small amount of a substance is to be dealt with, there needs to be a scale that is unimaginably large, so super, super huge, so that the amount will be significant and can be measured in the macroscopic or in real life. The most recent experimental value for a mole puts it at 6.022 times 10 to the 23rd things. That's just like 12 is a dozen. It's always that number. 6.022 times 10 to the 23rd is referred to as Avogadro's number in honor of the Italian scientist who came up with the concept. There can be a mole of literally anything, although it's really a big number, so it wouldn't make sense to count a mole of pens or a mole of big things, okay? A mole of pennies means that you have 6.022 times 10 to the 23rd pennies. Now, that's a lot of pennies, okay? I don't even know how much money that is, but it would be a lot. A mole of sand is 6.02 times 10 to the 23rd grains, and a mole of water is 6.022 times 10 to the 23rd water molecules. So no matter what we are talking about, if we have a mole, we have 6.022 times 10 to the 23rd of that thing. If carbon atoms were placed on a balance at one at a time, if we counted 1, 2, 3, and place them on our balance here, those carbon atoms, when we got to 1 mole, 6.022 times 10 to the 23rd, we would have 12.01 grams. Now, why is that number significant? Where does that come from? This is the number on the periodic table for carbon. So, coincidentally, a mole of a substance equals the number on the periodic table for the mass, okay? So, this information can be used in the reverse direction. So if we mass out 12.01 grams of carbon atoms, we know that that's 6.022 times 10 to the 23rd atoms, or 1 mole. This is what a chemist means when we talk about counting by mass. So we have a mass, but we can figure out how many atoms that is then. The term that makes this interconversion possible is the molar mass, which we'll learn about in the next lecture. The molar mass is of fundamental importance to chemists because it gives the mass of 1 mole of a specific object and therefore allows the conversion between grams and moles, so mass and numbers. So we can have a few things that this is the that a mole can equal. So a mole is the SI base unit for amount. It is also a conversion factor. Okay, we can use it to convert between things. It's what we call a chemist's dozen. So a dozen is 12, a mole is 6.02 times 10 to the 23rd, but you probably only really use it if you're a chemist, which you all are. 6.022 times 10 to the 23rd, anything. Grains of rice, sand particles, atoms, molecules, whatever we're talking about. Pennies. A magnifier between the atomic scale, so really, really tiny, and the macroscopic scale, something really big. See, this is why I needed a co-host. Zoom it in. The ratio of elements in a substance as indicated by its chemical formula. So those subscripts that we look at, if we have like CO2, that means we have 2 moles of oxygen to 1 mole of carbon. The ratio of elements combining in a chemical reaction as indicated by the balanced equation. So we'll get to this in a couple units. Actually, next week we'll get to that. And then finally, the sum of the atomic mass of all of the elements in a substance when the mass is expressed in grams. So what I was saying about carbon before, if we look carbon up on the periodic table, we mass out that amount, 12.01, we have a mole of atoms. If we mass out a mole of a substance, we just add up the number of, from the periodic table for each of the elements involved, and then we have the molar mass. And we'll learn about this in the next lecture as well. Okay, so we're going to do a little demonstration here, okay? And you are going to write down a few things. I'm going to move a couple things here. Get my marker. So we are going to mass out a dozen of a few things, okay? Got my, get that, maybe, nope, I'll get it. Okay, we'll go right there. We are going to start by massing out a dozen beans. So Mr. Strauss is going to put a dozen beans on our scale here. Okay. And I'm going to record for you the mass. These are the things you should be recording. So a dozen beans has a mass of 6.35 grams. Okay, will you switch over to a dozen toothpicks then, please?
Going everywhere.
A dozen toothpicks, 1.33 grams. Okay, switch over to the dozen pens. 11. Oh, where's my last pen?
We're one shy.
There you go, 12. A dozen pens. Don't let any roll out.
Everybody stay put. Stay.
142.72 grams. Okay, and finally a dozen rice pieces. Now these are super, super tiny. You can barely see them. Hopefully we didn't lose any rice pieces.
Nobody sneezed.
Okay, rice is 0.25. So I'm going to hold this a little closer here for you guys. Okay, what we can see is we have a dozen of each of those things, but none of the masses are the same. Okay, and the reason is those are all different things. Okay, so I want you to pause the video here. I want you to go ahead and answer those next few questions. I think there's like 6 of them. Okay, might need to look back at that reading that I did for a few of them. We're going to kind of reset here and then we'll be back with you. Okay, we're back. Hopefully you got those 6 questions answered. Basically what I wanted you to get at was that we measured the same count of all of these things, but they're all different masses. Okay, so now we're going to look at 3 different substances. Now I usually use different substances, but being that we are at home, I had to use chemicals that are readily available. So we have salt. Okay, salt is actually rock salt. We have baking soda, and we have just some plain old water in some really high-tech bowls that we borrowed from our son. Okay, and we've already put a bowl on the balance and zeroed it out so that we account for the mass of those bowls. Mr. Strauss is going to put each of these on here, and I'm going to record the mass again. So go ahead and do the salt first. So salt is sodium chloride. Okay.
That is 58.44 grams.
Okay, then you can switch to the water, please.
The water is 18.02 grams.
And the baking soda.
The baking soda is 84.00 grams.
Okay, so what we can see here, now those are obviously different masses. Now they probably have some sort of significance. And what that significance is, I want you to go take a look. Go use that Google machine and look up the molar mass of each of these things. Okay, what you should see is that each of these masses is equal to 1 mole of that substance. Okay, it's the molar mass. So what that tells us is that this large amount of salt that I have is the same count of sodium chloride atoms as this teeny, I wish you could see, this teeny bit of water. Okay, it's not very much water. It's only like filled to there. Okay, and it's the same count as this largish, and hopefully I don't spill it all over my kitchen, amount of baking soda. Okay, so all of these things have the same number of molecules in them, but they all had very different masses. Just like up here, all of those had the same count, right? They were all a dozen, but they all had different masses. Okay, what I want you to do is go ahead and finish out the questions on this part, write your summary, make sure you reach out to your teacher if you have any questions, and watch the next lectures for a little more information on a mole.